So I will not extend myself on this. I would like to invite the next speaker, talking on a very important topic. Lorenzo MALERBA. He is today working in Spain as a research professor, and is a specialist of materials. He used to work at SCKCN, and he is very aware of the European context. So thank you for coming, for all your effort, and please try to be...
Does this work? Yes. Okay.
Yes. Thank you.
So good afternoon, everyone. I have the task of talking about 6 projects. So my co-authors are the coordinators of these 6 projects. One is me, but then there is a... Does this work? Oh, okay. Thank you. So Pietro Agostini from Enea, who is also present here, Marjorie Bertolus, Fabienne Delage, Annette Gallet-Durand, Christian Grisolia, I don't remember her name, and Pierre-François Giroux, all of them from CA. They were either coordinators or helping the coordinators of the different projects that I will briefly talk about, of course, because I will try to be fast. I was very strict with my co-authors, 1 slide per project. But I will give a little bit the framework, and the framework is Generation 4 systems and fusion. So Generation 4 systems, we have been talking about them for the whole of the first part of the afternoon. And of course we know from also the talks that were given today, if we want to advertise what a Generation 4 system can do for us, can produce more fuel than it is consumed, can offer higher thermal efficiency, up to 50%, passive safety system, reduce the amount or the hazard of nuclear waste. All these are the promises of Generation 4 systems, but, yes? Okay, sorry. And so the problem is that materials will pay the price for this because we need to go to higher levels, higher temperature than in current systems, up to 1000 degrees C, depending on the system, in any case above 400, 500 degrees C. The irradiation dose will be higher in some components, and we cannot use water, so we need to use other coolants which are not necessarily nice to materials. There is an issue of a 60-year operation by design. The burn-ups will be very high, and they should include the possibility of burning minor actinides. All this produces significant stresses on materials, fuel materials and structural materials. Fusion, so thermonuclear fusion has a promise of being inexhaustible energy source in the long term. It promises very high standards of sustainability, efficiency, safety. Deuterium and lithium are the fuel, basically, because tritium is produced in the reactor by nuclear reaction with the lithium. They are widely available. The reaction products are inert, so basically the wastes that are a problem for fission do not exist for fusion. If we look at the nuclear reaction, of course, there will be other types of waste, for example, the structural materials around the reactor. But it is an energy a source of energy that is highly dense, like fission, so it can produce a lot of energy, and it is inherently safe. The main safety concern is in fact tritium, because the system as such does not have a possibility to diverge. But here as well, materials will be subject to very harsh conditions. In the first wall, they will receive thermal shocks on the order of several megawatts per square meter. The radiation dose will be high, tens of dPa, maybe not as high at least, depending on the design of course, but can be much higher for the moment in demo, at least not as high as in some Generation 4 systems, but still very high. Temperature, not as high in Generation 4 systems, but still high, 500 degrees C. And here as well, there are coolants or tritium breeders that are not water and that can be significantly aggressive for materials. So, in this framework, The development, qualification, and modeling of structural and fuel materials in connection with safety and efficiency issues are crucial to make nuclear energy, sustainable nuclear energy, a reality, whether it is generation 4 or fusion. And in some cases, there are issues relevant to materials that are common to generation 4 and fusion systems. So what I'm going to do is to give the highlights of 6 projects dealing either with structural or fuel materials for advanced nuclear systems, meaning by this generation 4, but also fusion. And 2 of these projects are explicitly cross-cutting between fission and fusion. And 4 of these projects are under the umbrella of the EERA-JPNM. So I will briefly, very briefly discuss what the EERA-JPNM is before going into the project. So EERA stands for European Energy Research Alliance. It is an association that currently includes more than 250 members, and it deals with all low-carbon energy technologies. There are 17 joint programs, each of them dealing either with a technology, can be solar, photovoltaic, wind, geothermal, and so on and so forth, or can be energy system integration, or can be materials. And one of the joint programs is the one on nuclear materials that I coordinate. The overarching, let's say, objective of the EERA-JPNM is to improve safety and sustainability of nuclear energy, focusing on materials. This means, on the one hand, to know better, to understand better how materials that exist already behave under the operating conditions that we expect in future systems. And if we understand this and try to model this as well, then we will be able maybe to find a new material solution, which can be new materials or can be new combinations of materials, or can be associations of design solutions with material solutions. There are many possibilities. The approach that is used is a combination of qualification, modeling, and development of new materials, with 3 grand challenges that are related with these 3 points. So to elaborate design rules and procedure for testing and assess materials behavior under the conditions that we expect in future systems. Develop new materials with better properties, especially in terms of resistance to irradiation, temperature, and environmental attack. And use modeling to support both of these activities. We have a strategic research agenda that can be found on the internet, and it provides a lot of more details, of course, than what I could say here in these few minutes. There are right now about 50 organizations involved in the EERA-JPNM from 17 countries, and each of them contributes to at least one of the 6 sub-programs. There are several sub-programs. Well, there are 6 sub-programs. There will be probably a new one soon, devoted to qualification, modeling, and development of structural and fuel materials. Having said that, now I start with the projects. So the projects were assigned to me. I did not decide which ones I was going to talk about. So Pelgrim is a project that belongs to the 7th framework program. It was, as I discovered, a long project because it went through, I think, 2 prolongations. And it is ended now. Here you can see each time I specify the budget of the project and the contribution from the Commission. There were 12 participants coordinated by Fabienne Delage at CA. The objective was to investigate minor actinide, by this meaning essentially americium, bearing fuels shaped as pellets or beads for generation 4 sodium fast reactors. And here is a very, very short summary of the main outcomes of the project. So both minor actinide, homogeneous and heterogeneous recyclers were considered. Both fabrication and characterization and behavior under irradiation were studied when the fuel was in the form of pellet or a sphere packed, so that they could provide a safety performance pre-assessment under operating conditions and also transient and severe accidents. different ways of producing beads have been explored, and the results on fuel swelling, fuel gas release, microstructure at different temperatures showed that there is no significant swelling in these fuels. All the helium is released, but krypton and xenon are releases temperature dependent. Overall, this is, as I say, a very, very short summary of the results, but the message is that the project has contributed to improve significantly the knowledge on americium-bearing fuel behavior for basically all the different concepts that have been considered for this type of fuels. Matisse is also an FP7 project. It also finished in 2017. Yeah, okay. This is a tiny detail of a single deliverable that because of a person who was sick could not be delivered. I don't think we should go into that. It's a bit... So, formally speaking, the project is closed. And, okay, this is the, again, the budget of the project and the contribution from the Commission. 29 participants, was in fact quite large, coordinated by CA. This project was really strongly related with the EERA-JPNM in the sense that it had two objectives somehow. On the one hand, to allow the EERA-JPNM to become better structured as a platform. So this was maybe something for a coordination support action, which was in one work package, and also fund the research that was underway within the EERA-JPNM. So this is how the Matisse project was conceived. And so this project was the reflection of the structure that the EERA-JPNM had in those times. In 2013, there were 4 sub-programs. Fuel had not been yet introduced. There was materials qualification for ESNI in high temperature steels, refractory materials, and modeling. And correspondingly, there were 4 work packages, okay, reshuffled in terms of order, but they contained all the activities. In fact, in practice, it is almost as if each work package had been a project in itself, because it really covered or tried to cover all of the aspects that were addressed within the JPNM, meaning that there was a very strong in-kind contribution, which in fact goes also beyond this 8.6 declared. And I would say there are too many results to be summarized, because if I wanted to summarize the results, I should go into each of the work packages, which are about a significantly different topic, and go into the result. There are actually a large amount of very interesting results within Matisse. Gemma is an ongoing project, so I can mainly tell what it is about, because of course it started in 2017. It is coordinated by Pietro Agostini from ENEA, 23 participants, and you will see that more or less this is always the situation that I've seen. This is typical for other cases as well, even though in Horizon 2020 we are entitled to ask for 100% reimbursement, but the decision was not to do so, and to always have part of the budget that is in kind. So Gemma, which stands for Generation 4 Materials Maturity, deals with specific and important Generation 4 material issues, reflecting the EERA-JPNM threefold approach to material studies that I presented before, and here it appears again: characterization, modeling, and new materials. So this approach is translated in the case of Gemma. You can see it here. This table summarizes very well the way the project is organized, because you have characterization in view of codification, modeling, and innovative material solutions. The 3 of them are in the project in different work packages, depending on the 2 main issues are addressed: compatibility with coolants and neutron irradiation effects. So concerning compatibility with coolant, there is a huge amount of activity of characterization in work package 2 and 4, one on welds and the other on base materials. And there is also some part of modeling. There is a fully, let's say, modeling embedded activity on neutron radiation effects on materials for cladding in SFR. And there are new materials, alumina forming alloys that are studied in contact with lead, especially lead and lead bismuth. So a very large amount of data are being and will be eventually generated. The idea is to be able to deduce from there useful rules for systems and component designers. And the data, the idea is also to express them in such a way that they can be included in the design rules of the RCC-MRX code eventually. They will be stored in the JRC repository MATDB. INSPYRE is somehow the twin project of Gemma, but for fuel. So these two projects they are not similar, but they have the same type of objective somehow, which is to provide important information about materials for Generation 4 systems. INSPYRE is coordinated by Marjorie Bertolus at CA. Here there is, you see, a big in-kind contribution, 14 participants. It is at the same level as Gemma. It started in 2017. It is embedded in the EERA-JPNM, and there are a few strategic objectives that I will summarize here. So the idea is to make a major breakthrough in understanding and describing fast reactor MOX behavior under irradiation in several conditions by using an approach that is quite fundamental. So separate effect experiments, multi-scale and thermodynamic modeling, and of course use also of post-irradiation examination results on neutron irradiation fuel from previous campaigns, so to make use of available experimental data. The focus is on 4 important operational issues: margin to fuel melting, atom transport and fission product behavior, mechanical properties, fuel thermochemistry, and interaction with the cladding. And the idea is to develop predictive capabilities that should be transferred into fuel performance codes. So this means to transfer knowledge that has been acquired maybe with fundamental models into the performance code, and also based on the fact of bringing together experts that should agree on what should be done to improve the quality of the fuel performance codes. And there is also an important effort of training. It is there in all projects, but here I would say INSPYRE has put really a lot of emphasis on training next generation of researchers. M4F is the project that I am coordinating. Actually, I inherited it when I moved to CMAT. You see it's the usual more or less ratio between the contribution and the actual budget. There are 20 participants. It is embedded in the EERA-JPNM, but not only, because one of the objectives of this project is to bring together fusion and fission materials communities, to have a dialogue between experts in fission and fusion materials. In many, many cases, they are actually the same person with a different hat. In some cases, they are different persons, and in some cases, it is surprising, but the people from fusion do not have any clue about what has been done in fission, and vice versa. And this is a good opportunity to close this gap. Specifically, the project is not on all fusion materials, of course. It will focus on the intersection between fission and fusion materials, which are ferritic martensitic steels that will probably not be used in most of the prototypes or demonstrators for a number of reasons, but are expected to be useful as the materials for the future Generation 4 systems, and they are essentially the only choice for fusion. And there are 2 specific aspects that are addressed in the project. One is the problem of so-called localized deformation, which I'm not going to try to explain now because I would need 3 or 4 or 5 slides, but it is an important problem, especially in connection with the design codes, because it is something that happens in these materials, does not happen so much in other materials. And the The other point, which is also important, and it is much wider than just, let's say, ferritic martensitic steels, is up to what extent and whether or not we can design a sort of protocol to use ion irradiation as a tool not to replace neutron irradiation, but to support. It cannot be used for qualification, but it can be used for screening, for example, of new materials, or to understand what is going on with a given material. And the approach that is used is multi-scale modeling, meaning that we use different simulation tools coupled with microstructural examination to understand what is going on at the level of the material's evolution under irradiation. And finally, TRANSAT. Okay, we have here the coordinator if you have questions, because I'm not expert here. Coordinated by Christian Grisolia, CA. All these projects started at the same time, basically in the same moment, so less than 2 years ago. In this case, TRANSAT is a cross-cutting project also between fission and fusion in support to improve knowledge on tritium management in fission and fusion facilities. And these are the 4 issues that are addressed: tritium permeation control, assessment of the tritium inventory using state-of-the-art modeling tools, engineering solutions for detritiation techniques and waste management, refinement of the knowledge on outgassing, radiotoxicity, and so on. And here we have a very nice scheme that shows how these 4 issues are connected with each other in a chain, and all of them will, of course, contribute to the part on dissemination, communication, and stakeholders. So to conclude, I'm not going to reanalyze all the projects, but I think that what we, let's say, the message that I want to try to convey is that for what concerns nuclear materials, especially for future systems, the EERA-JPNM has managed in the last few years to coordinate the European activities on qualification, modeling, and development of structural and fuel materials. All the projects that you have seen, and also, in fact, other projects, are the result of a bottom-up alignment of national projects. Basically, even before these projects were proposed, let's say, to be funded by the European Commission, at least partially, they had already been started, launched, defined, meaning that we had already our roadmap, if you want. We knew what we wanted to do, and we had, sometimes we were lucky, sometimes maybe we were good, and we could use the opportunity given by the European Commission to put the hat of not only some money, but in fact, as Kevin Motors had said the first day, it is very important to have a legal framework, which no, let's say, initiative taken between different organizations in different countries will never have in such an efficient way as a European project can have. So you are obliged to provide your deliverable. If you don't provide the deliverable, Nicola will say, no, the project is not finished. This would not happen if we were just agreeing between each other about what to do in a sort of in-kind way. So in that respect, it is very useful. But this is integrated by institutional funding in all cases, in all the projects. So we think that this provides solid basis to build a European Joint Program on Nuclear Materials, which is in the current program. So we are preparing it together with Nuginia. And also, it is important to say and to see that fission, fusion, cross-cutting projects can be a valid instrument to optimize the use of resources, benefiting from cross-fertilization, giving, as I said, for example, the opportunity for people from fusion to discover that some things have been done in fission and they didn't know about it, and sometimes vice versa as well. And there are several, concerning materials especially several topics on which fission and fusion can valuably collaborate. There will be a workshop tomorrow on this topic. So thank you for your attention.
Thank you, Lorenzo, for this comprehensive presentation. And I think for me, looking forward to some cooperation, fission, fusion, non-nuclear energy materials is an issue for all of us. Any question?
Yeah, Lorenzo, I'm a bit surprised by the statement you put that there is such a strong separation that fusion people, the material doesn't know about what we need from fission and vice versa. Because in many organizations, at least the medium-sized one, the people are in the same offices, so to my opinion, they are communicating. So is it then a sort of statement that you are making in general, or is it that strong statement?
It's a statement that I'm making in general, and I agree with you that in small, medium research centers, the people not only are in the same office, they are sometimes the same. So in that case, of course, there is knowledge of what is going on. I had the chance of being in that position, and many people at SEK, for example, are in this position. But it does not happen everywhere. And especially when the center is large, and they are maybe, sometimes they are in totally, the case of CMAT, where I'm now, they are in two different departments. So in those cases, I can assure you, they don't know anything about each other. They don't talk. They ignore that some problems that have been clearly identified in fission, I don't want to say solved, but at least identified and studied, and that suddenly in fusion say, oh, there is this problem. What should we do? And a lot of work has been done in fission, and they didn't know. Being in the stack of Eurofusion, I realized that this happened too often. It should not happen.
There's nothing specific to nuclear. No. Just a question of people, the way the organization is running, and I think if the management is looking or tackling these issues, then it is that the communication takes place. Okay, any other, a quick one, because we have to.
Hi there. Quick question on the scope and the aspect of what's your thoughts on instrumentation, materials used in sensors and things like that as well. I'm wondering, is that an area that could be involved in this, or is that involved already? Is there collaboration there potential?
So, up to now, at least within the JPNM, of course in Virginia there are activities. In the JPNM we have never considered those aspects, but we are going to do that. So we are going to open a new sub-program exactly devoted to these aspects, because we realize that they are important aspects also for advanced systems, not only for existing reactors. But it is true, up to now it is something we have somehow neglected, so we cannot say anything about it.
Okay, thank you, Lorenzo.